So before going deep into details about predictive analytics, a few words about myself. I have an academic background. I've used to do data mining, machine learning research in various areas. And then I was working for a startup as a data scientist. So I had the theory first, and then some practical use of machine learning, predicting user behavior. And right now what I do is I'm one of the founders of a startup called Hadoop. This is a graphical user interface for big data analytics. So with no programming, you are able to perform analytics. It's based on RapidMiner, which is one of the most used and most widely used advanced analytics tools. So this is what I do, and I talk to a lot of customers and a lot of people interested in doing predictive analytics on Hadoop and large-scale predictive analytics. Many times they are confused. Even predictive analytics itself is a complex topic, but running it on Hadoop and having it in a big data environment just adds to that. What I want to cover today is, in many cases, it does not really matter. So most people think that the more data you have, the better model you will achieve. And it's sometimes true, but in many cases, you can get faster results and you can get better models even if you stick with your single node tools like R and Python, or use some in-memory tool like RapidMiner. So first a short introduction to predictive analytics. I will try to cover 4 different fields today. One is recommendation, anomaly detection, clustering, and classification. So a few words about each of these. You have probably heard about recommendation in other sessions, but the basic setup is that you have different users with different taste profiles. So it can work for movies, books, whatever that has taste aspect in it. And you have certain users with who expressed their interest in several movies, for example, and you need to do a prediction, kind of a recommendation. What item should that third user consume? What is the best prediction for him? And there are pretty neat algorithms to do that. I will talk more in detail about how scaling up such a recommendation problem would help your results. The next one is anomaly detection. This is kind of a broad field. Anomalies come in many forms. So, for example, in the financial industry, it usually comes in the form of fraud. So someone is trying to steal your money. In other areas, it might come as some kind of error with some machine or some data collection error. So there are various algorithms to address that. And big data is known to be very powerful in this area. The next one is clustering, when you are trying to find groups in your data set. So for example, if you have users, you're trying to do some kind of segmentation and find different target groups for marketing. That's a very common use case. But clustering can also help other forms of predictive analytics. So if you can find groups who behave like each other, then you can use that information in other models. For example, in recommendations, it's a very useful input for the recommender. For example, having a clustering result. The next one is more broadly called supervised learning. When you have a classification or regression problems. For example, if you want to predict if a customer will leave your company or not, so if he will churn or not, then you have lots of historical data on that. So you know who left your company last year, so you're trying to make predictions this year so you can avoid that maybe with a personalized campaign on that group. So how it works, you usually have a data set which includes labeled true or false if those users have churned or not. and we are trying to find kind of a rule set, a model from that, a set of rules that you can use for your current situation and do a prediction for your current user base. Regression is also similar, but in that case, you're not predicting some binary output like churning or not, but you are predicting some continuous variable, for example, the price of the stock tomorrow. So there are various algorithms to address that. And these are the 4 fields that I want to talk about today and cover how they react to more data, and does it make sense to use more data to address these kinds of predictive analytics problems. But to get into that, first, let's see what tools are available, because most of us are not creating these predictive analytics algorithms. We prefer to kind of reuse some of the tools that are available, some libraries, some programming languages which are good to address these problems. So for example, R and Python are very popular to do data science these days. And also there are some graphical interfaces like SAS, RapidMiner, and some others. So they usually work on a single machine. You just load up your data, it stores it in memory, and you can use hundreds of algorithms from the predictive analytics research. What they have accomplished in the past few decades, you can use those algorithms and run it on your data set. On the other hand, we have several new tools like Mahout. Spark has a machine learning library, or GraphLab. These are more like these scale-out architectures. These are created for the scale-out architectures like Hadoop, and they can address very large-scale learning problems. And in case your data set does not fit into the memory, then they provide several algorithms. Of course, they do not have such a long history, and these tools are usually a few years old, while for example, Veka has been available for like 20 years. So I will just mark these tools. On the left-hand side, you can run them on a laptop, and typically what's on the right-hand side, you run it in a data center in a cluster of computers. So these are 2 very different kind of libraries that you can use, and these help you so you do not need to program complex mathematic terms. You are just using some APIs and using some libraries or even graphical interfaces to solve your predictive analytics problem. There has been a big debate on either, so if you need more data to solve the predictive problems better, to have better predictions for the future, or you need better algorithms. There's a famous paper on that. This comes from some really high-profile people from Google that says this unreasonable effectiveness of data. And they state that for most of their problems, most of the Google problems, they see that they do not need to spend lots of research time and do not need to have many PhDs to create more complex algorithms and improve the accuracy, for example, for those algorithms, but they prefer to use more data. And it's most of the time it's beneficial for them. They get better results if they have more data compared to having a more complex algorithm. There's another paper recently. This is kind of academic papers, which was only published a few months ago. And they have also checked with different data sets what happens if you increase the size of the data. And they concluded that in most cases, your predictive models get better and they will improve. So the main message from these papers is that if you have certain amount of data and if you have some basic algorithm, then you may have 2 different choices. Either one choice is to collect more data and still use the same algorithm, do not spend much research and engineering time on coming up with more complex algorithms, just have more data. And the other path is to have the data that you have already and create more complex algorithms, improve your models, improve your predictive analytics algorithms. So in this case, both of these papers state that you should go for more data. That's the better way. It will take less time for you, and you will get better results. And I completely agree with that. So this is a completely valid statement. But as a side note, all the problems that they have phrased are typically high-dimensional problems, where you, for example, text mining, where each column is a different word. So you have tens of thousands of words, for example, on the web. So it's very high-dimensional and usually very sparse. So for most of the records, you have lots of zeros in there, because not all words are happening in all documents. So all the problems, they also covered some image mining, image recognition problems. All of those problems are high-dimensional and sparse. And on the other hand, I believe that this is not the dilemma that we usually have as a data scientist or some analyst. Of course, at Google, you usually have the flexibility. So if you want to collect more data, you can go back to the engineer and tell him that implement some more data collection in the system. But at a lot of companies, you just cannot control the data collection part. You have some amount of data, and that's it. You should decide what to do with that. You cannot control the whole process end-to-end, from data collection to having the business results. So the dilemma that you usually have is that I have certain amount of data, and I have two ways to go. Either, if it's a large data set, then either I will go with these multi-node algorithms that can scale out on a cluster and spend lots of engineering time to work with all the data. Or another path may be to kind of subsample the data, so reduce the size, and just use all the usual tools that are available on a single laptop or a single server, and use R or Python or some other components. So I believe this is usually the dilemma, and what I would like to cover today is which way to go for different predictive analytics problems. So let's go into recommendation first. So how does it look like from the algorithmic perspective? What is the data that you are working on? You essentially have kind of a matrix where you have a single row for each user and a single column for each item. So for example, for each movie, you have a column. And you have several ratings or either some binary identifiers that this user has watched this movie and watched it till the end. That's also might be interesting to if it was stopped in the middle or if that user watched the movie till the end. So you have these numbers in this matrix, but it's very sparse. So you have lots of missing values in there. So actually, this is the kind of problem that the Google guys have been talking about. So this is high-dimensional. You usually have thousands, tens of thousands of items. And it's sparse. For each user, you maybe have a few hundred ratings. And this is exactly the problem that they had. And here, this is the case that the more data you have, the better results you will receive. And there is quite a famous story about the Netflix prize. Netflix, I'm sure that most of you know Netflix. They had a data mining competition a few years ago, and the grand prize was $1 million. And the goal was to improve the recommendation algorithm by 10%. And actually, after 2.5 years, with lots of research and engineering effort, there was one group of people who achieved that. But the funny case is that algorithm never got into the Netflix production system. It was just too complex, too hard to maintain, and it wasn't worth it to have a more complex algorithm for 1 or 2% of accuracy. So they instead went for simple algorithms that could scale and that could be productionized. So more data was very helpful for them, and they did not want the very, very complex algorithms. They have just stopped at level of complexity to reduce the maintenance and operational complexities. So what is the recommendation for these types of tasks? Well, basically, if you have a lot of data, then yeah, you should go with the multi-node environment. You should use Mahout, you should use GraphLab. Those are great tools and quite stable. I would say that the recommendation algorithms are very good in all these components. So the 10 million limit, so 10 million ratings we are talking about, is recommended by the Mahout wiki page. I would say it's probably tens of millions where you have this limit. But yeah, as soon as your algorithm seems to be slow or seems to have some problems on a single node, then you should go for a multi-node environment. You will benefit from that. So you should not subsample it. You should use all your data for recommendation. Let's see anomaly detection. It's a very broad area. So what is anomaly? It really depends on what is considered normal. So you cannot tell what is an outlier, what is an anomalous behavior until you have not defined what the normal behavior is. So typical causes might be that there is some collection error, some data collection error. For example, some sensor got broken and it's not measuring the temperature anymore, but it has some bad value that it outputs. What you can do is just simply exclude that data because you cannot fix the hardware after the data collection happened. So another potential problem is you simply, you have these ETL processes. You are loading data from one system to another. You are doing conversions with the data. It might happen that you make some error, implement some error in that process. So while you are converting the data, you are missing some values. You can go back and fix that, so that's easy to do. But we are really interested in is some real malfunction, some real error, some real fraudulent behavior that we want to recognize and create an alert on that. So if it's financial fraud, then of course you want to know about it as soon as possible. And there are two ways to address these, probably even more, but two main groups of ways to address these kinds of problems. One is the supervised way, when you have historical data on fraud, for example, on fraud events. So you know who cheated last year, and you want to build a model to predict the same kinds of fraudulent activities this year. Of course, it's not complete, because if someone comes up with a new type of fraud, then you won't recognize that. So in most of the cases, unsupervised detection is preferred. When you're really looking for outliers, looking for events that are not normal, not typical, and trying to recognize those. So because of this, you usually have a large data set. There's a lot of normal activity. And there are a few interesting records, few interesting data points which are covering some kind of anomaly. In case you are going with supervised and you have labeled examples from the past, what has been anomaly and what hasn't, then you may do some sampling. So you have few anomalies, but you have lots of normal events. You can just reduce the amount of normal events because they look the same anyway, so they do not contain a lot of information. In that case, you can reduce your data set and go with a single node tool. That's completely fine. But as I said, unsupervised methods are better in some sense. In that case, you cannot really leave out data from your data set because you might be leaving out an anomalous record, so you won't be able to recognize that. So in most cases, you also want to go for multi-node environments if you have lots of data. In this case, I would say that 100 million values, which means that if you multiply your rows and columns, then you get the number of values that you have in your data set. I would say that around 100 million, there might be a limit where you can stop using the single node and probably move to a multi-node environment. So far it seems that the Google guys have been right. So if you have a lot of data, you should use them and you're better off. But let's see some examples where it might not be the case. So in terms of clustering, there are different types of clustering. Probably most of you have heard about k-means. It's a centroid-based clustering, so you are storing the center of each cluster, and that's what you want to find and want to optimize. There are also other distribution-based, it's very similar, but there are also other methods. The problem with other methods is that they usually do not scale. So those methods, hierarchical, density-based clustering, those are typically cubic or quadratic in terms of the number of records. So if you are using large data sets, you of course do not want cubic algorithms, because having twice as many records will result in 8 times more runtime and 8 times more resources. So that doesn't scale at all. So the first two categories, the centroid-based and distribution-based algorithms, are typical in large-scale environments. And what you do in these methods, you're always estimating some parameters. So most of the time, you're estimating the mean. So in the k-means, for example, you have a group of items, and you're looking for the mean of the centroid of the cluster. And in case you are estimating the mean, you have some estimation properties that you should keep in mind. So, for example, if you want a very strong estimate, that means it's 2.5% of the standard deviation. That's very close to the real value. And you want to be 99% confident that it's there. Then you only need 10,000 examples to achieve that. That's not that much if we are talking about big data. So if in a single cluster you have more than 10,000 examples, it might make sense to simply subsample it, and just keep 10,000 of those, and you will still get a very, very good estimate on the cluster centroids. It does not deteriorate the model performance at all. On the other hand, if you have lots of dimensions, and we are getting back to this high dimensional problem again, you are estimating the mean for each dimension. So, okay, I'm 99% confident that one of the dimensions are accurate, but if I have to say that there are 2 dimensions, then for each of those, I'm 99% confident. But for both of those, I'm only 98% confident. So as it increases, the number of dimensions increases, your confidence increases in your estimates, decreases with your estimates. So a good recommendation would be for clustering is, of course, again, if you have less than 100 million values, then you should go for single node. There are pretty good algorithms that can calculate your clustering on a single machine. If you expect that your data set will contain small clusters, then you cannot really subsample, because you will lose many data points from those clusters, and it will change the result, and it will be very unstable what the result might be. So I would say that if you are expecting smaller cluster than 10,000 records, then you should not do any sampling, because it might change pretty much where that cluster will be and how it will behave. And also, if you have many features, in this case I was using 10, if you have more than 10 features, then you should probably also not subsample, because your confidence is very low on the mean estimate. So in those cases, you should go for a multi-node environment. And if you can do this subsampling, so for example, you have 3, 4, 5 dimensions, and you have millions of values and looking for 5 clusters, then you will usually have very large clusters. You can subsample that, and decide after subsampling. You can again decide if it fits on a single node, or if I still need to go to the multi-node setup. So I think there's a huge blind spot when people are using Hadoop. Your data resides on Hadoop, and you want to solve every problem with Hadoop. But it probably doesn't really make sense, because your result will be the same if you just subsample for clustering and run it with some good algorithm in Python or R. The next one is even more tricky, the classification problem. So there are many different supervised learning algorithms. Several of those are listed there. So, for example, naive Bayes. That's also working with estimates. So it's also estimating the means and the standard deviations of different clusters. So here you could have the same argument like we had for clustering, that from a large enough sample, we could be able to estimate these parameters quite reliably. Also, there are other models like decision trees, where you have the whole data set and trying to find splits on that data set. So your labeling, your prediction becomes better as you go down the tree. In this case, you can also imagine that if you have lots of records in one of these leaves and you want to split that, it does not really matter the performance of that split. It doesn't really depend if you have 1 million records or 10 million records. So at some point, you could do some sampling and it would still have the same split in the tree and you would still get the same decision tree at the end. And also there is a random forest, which is a group of, which is in the group of ensemble methods in machine learning. And actually these kinds of methods use sampling internally a lot. So what random forest does, it builds multiple decision trees from the same data set, but for each decision tree creates a small different sample of the original data set. So for example, it selects several columns of the data set. It's not using always all the columns, but for each tree there is a subset of the columns that it's working on. And it's also subsampling the records. So in most of the cases, random forest, when you build multiple decision trees, a single tree will easily fit into memory. So it uses inside a sampling technique, and it increases performance. So it seems that we have, of course, there are many more algorithms, and it seems that you always have a different criteria on how much data to use for these algorithms. So we should take another approach and try to find out if a certain algorithm would benefit from more data. And what helps with that is the learning curve. A learning curve is a graph that, you cannot read that. So on this axis, we are increasing the size of the data set. The blue line is the training error. So you split your data set to training set and test set. On the training set, you are building your model, so optimizing the parameters, trying to find the good splits for the decision tree. And the training error usually increases with the size of the data set, because when you have very small data set, of course you can build a decision tree on that. Each record will be in one of the leaves of the tree, and you will get a perfect classifier on the training set. However, it will overfit your training data, and it will not work on new unseen data. So usually in the beginning, you have very small training error, very large test error, because you could not generalize the patterns and the rules in the training set. So as you go forward, your training error is increasing, and you are trying to fit a better model on the data set. In the same time, your testing error is decreasing because you are finding the good patterns in the data. So as you can see here, if you have a learning curve like this, then you can see that these errors are very close. So the training error and the test error are very close. So you could not expect that your algorithm will perform better on the test data than on the training data, because it knows the label, it knows the predictions for the training data. So if it's so close, you cannot expect that the training error, the test error could be reduced significantly. So the green line cannot go lower than the blue line. Of course, sometimes if you have few values, then because of noise it can. But if you have meaningful, large test sets, then it never happens. So seeing this, you should expect that no matter how data I provide to this algorithm, it will not improve anymore. So it's kind of a plateau. It doesn't matter if I throw in like a million times more data, it will likely have the same accuracy, the same result. On the other hand, if you see learning curves like this, you see that there's a huge potential here that you can improve your test result. So in this case, if I would add more data and continue this chart to the right, then likely I will get a better model, lower error rate, better accuracy. So it makes sense to use more data for this particular algorithm. So we could not decide on a general rule on when to use more data for classification, but if we just pick a small sample that fits on a single node from that data set and draw the learning curves, then we could get a pretty good idea on how low our error rate might be and if there's any potential to improve with more data. So if you see this one on the right, then you should go for a multi-node environment and have a large-scale classification system in place. In case you see this, then it doesn't make sense to spend time with configuring Mahout and spending weeks and months on improving and running a large-scale classifier because it will not improve your prediction for churning customers and have no benefit of doing that. So this is the recommendation again, that if you have limited, if you have an amount of data that fits into memory, then you can use a single node. Otherwise, you should plot this learning curve and see it for yourself if it makes sense to scale out your algorithm. So again, I believe that this is a huge blind spot. There are many people doing these kinds of problems with Mahout and with other machine learning libraries on Hadoop. It's just simply a waste of effort, and there's no upside for the company. Of course, all these rules seems to be quite strict, but I do not mean them to be strict. So, of course, if you have a huge server with lots of memory, then your limits might be different. But I think these decision trees kind of really could help you to think about how to address these predictive analytics problems and probably come up with still the best models, but with less effort if you do not need to go for a large-scale implementation. So with that, thank you for your time. As I see, we have 6 minutes for questions if you have any. Lots of people taking pictures. Yes?
My understanding is that random forest, for example, can be very easily distributed because evaluates the part.
Yeah.
Basically, it's a good idea to distribute it even to gain some performance when it's not purely needed regarding the time.
Yeah, it might make sense from the performance point of view, because on a single node you would typically pick a sample from the data set for a single tree, run the tree, and then do it again. So you do it serially after each other. And in a distributed environment, you can do it in parallel. So each node is working on one of the trees on one particular data sample. And yeah, that makes a lot of sense. Yeah, but at the moment, I would say that all these random forest implementations are not that easy to use. So you need to balance. Of course, you can get a gain in the time needed to run the algorithm, but on the other hand, you would likely spend more engineering time to set it up. So it depends what you have, time or computing resources. Yeah, I would say it's not that easy. And even, for example, Mahout has a random forest. I have not found it very stable at the moment. So yeah, for some problems and some data types it works, but for some it doesn't.
You know about the data versus model slide. You prefer to use more data in a simple algorithm.
Yeah.
If you have high-dimensional sparse data, it doesn't make sense to use a complex specifier at all. I would say for a high-dimensional or small amount of high-dimensional sparse data, it's also better to use a simple algorithm.
Yeah.
So is it always better to use a simple algorithm?
For very high dimensional data, yes. You usually do not, because for usually for each model, for each attribute, you have some kind of parameters that you're trying to tune. So if you have thousands of attributes, thousands of dimensions, then your model itself, even if it's like a naive Bayes model, some very simple, then it have thousands of parameters. So to learn thousands of parameters, you need lots of data. So if you even want to complicate that, then you need even more because you have more parameters. You need even more data to get a good estimate for those parameters. Probably complex algorithms do help, but in a very, very large scale. So it's not your scale, not my scale, but Google scale. Yeah. Yeah, certainly there are some algorithms which do not scale at all because cubic, quadratic runtimes. In that case, what I would do first is see the learning curve of your preferred unscalable algorithm, see what the performance looks like, and you set your expectations what those learning curves might become far away with large data sets. And start trying simpler models and see the learning curve for those. And you can see if there is any potential that those simple algorithms will reach the same result with large data sets or not. This is a well-known problem in machine learning. It's called the bias and variance dilemma. You can read about that. There's no silver bullet. You should always experiment and see for your specific problem what works or not. Any more questions? Okay, then. Thank you and have a nice day going forward.